when smoothing fails. Okay, so now we're gonna address this first question. So now we're going to take, and since we didn't go through construction, this is kind of meaningless, but this K1/A1. So we've taken the first step of this process, this algorithm, Benedetto's, and we turned in another crank, right? So in theory, this set should be closer to an orthonormal basis. So let's see what happens when we smooth it. So we have this set right here. So we're gonna start with the same function we had before, that box function that is getting narrower and taller as we increase our m's. And we have this very surprising result. We never get a frame for any m. Any m we choose, not a frame. We do get a Bessel sequence though. We do get a Bessel sequence. And this Bessel sequence, we can approximate the upper frame bound. It's between this, but even then, yet again, there's a point like it never goes lower than this 305 to 256. It's just sitting somewhere between these two bounds.
So what do you lose when you lose that A?
Well, so let's think about this. Let's look at this definition again. So what do we have? So for the A. Well, so maybe, okay, so we're looking at F squared. Okay, so what happens if there's not an A? Well, obviously, anything we put into here is not going to be negative, right? And all we need A to be is non-negative. So what that means is that if no A greater than 0 exists, then there exists some sequence of functions where basically we can assume that the norms are all 1. But if we take these inner products, this goes to 0. So maybe that's what the person who said content was trying to say, is that basically you get functions here that you're basically losing if there's any information whatsoever, because the information you're getting is going down to 0, even though these functions you have are not. So that's why not having a lower frame bound is bad.
Basically, you lose reconstruction.
Right, right. Of course, you could lose that without the B too, but this is kind of a specific reason for A. You're just kind of getting things disappearing off.
Just as a quick aside, just something that comes to my head, might you only lose that on like a small set? And I mean, are there conditions where I'm thinking like a fold in a space, you know, on a surface, like you might hit like a fold or something where you lose that in a special case, but generally speaking.
I mean, that definitely could be, there could be almost like there's a dimension where things are going wrong. And a loose way of thinking about
Okay.
things. So yes, that's true. There might be, you might just be able to throw out some stuff, and then what you get is all right. But you have to know what to throw out, and then you still won't be representing the entire space anymore. You're only representing a subspace.
But you might not have a subspace that just goes straight to 0.
Yeah, but you might have a subspace that contains the things. It's not guaranteed, but that might happen.
Yeah.
But then you're losing a representation of your entire space. So unless those things that are kind of tending off to 0 are things you don't want to consider in the first place, then this would be a problem. Okay. So, and I guess I should mention, basically yet again, just the power of approximate identities. I was actually able to, you can show that this is not a frame by using functions that are kind of built up by a linear combination of approximate identities to create unit norm, but you have this conversion to 0. Okay? Yes, I just said that. Okay, good. Okay, so how do we fix this? So one of the ideas was like, all right, so we've got a couple problems here. We're not getting exact. We're not always getting frames. We're starting with partial frames. We're not always getting frames, and even if we do get frames, we can't figure out necessarily what the exact lower frame bound is. So is there something we can do where we can change things? And the totally non-intuitive method is, okay, you know what, this is probably at this point in night too many words. Just go down to this, basically. Basically what we're going to do is if you have a function and the support of that function is contained, say, in -1/2, 1/2. And the support of the function has like a hole around the origin, then basically what we're going to end up getting, we're always going to end up getting a frame. So that was kind of the end way thing. Let's go through this. Yeah. Oh, oops. Okay, that's for the paper. Okay, so this is saying this delta L here is you take the set L and you look at all the integer translates of L. So integer lattice here in higher dimensions. So delta L is defined to be the distance between L so we have our set L and we shift L over 1, 0, -1, 0, up, and we say what's the distance, like what's the closest L gets to any of its translates. The reason this ends up being important is so if we go back to that canonical so let's go back to that canonical example. Which was basically kind of the shrinking that little boxy donut down. Okay, so this, let's call this set. I'll fill it up. Then this, what is the delta of L going to be? What happens when you shift this, say,
0.
right, it's going to be 0 because it touches, when you shift it touches itself. So basically what happens is if we, just with some of the computations that we have using those restrictions and bounds and other things, if we now have it where, let's say we shrink this down a little bit more, so if we shrink this down a little bit more, so now we have L prime, and we're looking at this.
You have to make the whole bigger.
Well, let me think if that would work.
I think you have to, or it'll always be 0.
No, that I can say for sure is not true because this, we shrunk this down, and this delta L of prime
Oh, okay.
is going to be
Right.
what 1/2 now?
Yeah.
So sorry, 1/4. This is a -1/4. Move it up one, so we get so basically what was kind of going on, and to hand away since I've got another argument that makes this a little more Okay. Let's do this first. It's probably a better place to have this slide because then it gives you a little more intuition. Because without you guys having those formulas right in front of you that I'm basing all these bounds on, that this kind of argumentation seems kind of meaningless. So let's just go with this argument right here. So, okay. So basically, what are we doing? The shrinking argument says what we're going to do is we're going to take some sort of function that we have. So we have a smooth partial frame wavelet set, and we're just going to shrink it down. We're going to shrink it down on its support, and I'm going to say that given certain hypotheses, that we're actually going to now get something that is a frame. So why should this work? So okay, so we start with some psi and L2, and we define phi hat to be equal to psi hat gamma of alpha, psi hat of alpha gamma. So basically we're on the frequency domain and we're shrinking this frequency down. We're shrinking this support down. So it's like here, if we have the support is this, we're now shrinking it down so the support is this.
And this is all being done on the frequency side?
This is all on the frequency side. Sorry, so I guess I wasn't being very clear before. So this is all, like, basically all the work that's been done on this is on the frequency side. Okay. So the Fourier transform of F, so this looks very complicated, but it's basically, if you take the Fourier transform, so we have the Fourier transform of this Fourier transform interacts with dilations in a certain way, and this is the way it interacts. So we know that phi then is the inverse Fourier transform times Fourier transform of phi. And we know that phi, or Fourier transform of phi is equal to this thing right here, which could be rewritten like this. And basically we're just kind of doing hand-wavy stuff. There's certain formulas you can move around a Fourier transform and this type of dilation, and all it takes is U substitution. You just take the Fourier transform and you use U substitution from calculus to get this. So we end up getting this right here. So now when we take the systems of dilations and translations of this phi, we get this right here, which looks messy, but if we have, let's say we used alpha, so we dyadically shrink this, say, right? So then if we plug this in, then, okay, well, log base 2 of some alpha, then we now have n minus some integer. So all we're doing is we're saying that we're dilating by every single integer shifted by a set integer, so that's the same thing as dilating by everything, right? You dilate by every integer minus 1, it's still the same thing as dilating by every integer power. So basically we can rewrite this and we can see that the span of this dilations and translations of phi is equal to the span, I'm saying span so that these coefficients don't really matter, it's equal to the span of the dilations with the translations by k divided by to the n of phi. So what are we doing? Dyadic shrinking, you can think of it as we've now taken this wavelet system that we started out with. I always raise something. This is what happens when you haven't practiced that before. So it wasn't a frame, which means basically we were getting functions that were going down to 0. We weren't picking up enough information about the functions. So that was the problem. That's what was causing us not to actually generate a frame. So now what we're doing is we're adding in more information, right? So we've now doubled the number of coefficients we're going to get. We're going to take all of the coefficients we would have by just taking dilations and integer translations of psi, but now we've added all of these other translations on top of that. Does that make sense? So we're now taking so we now have we're looking at this EJ squared. There's more of these terms, so it's less likely to be 0. It's less likely to give us that problem, and that's what's causing the problem before, is it keeps going down. And even if it's not, even if alpha isn't a dyadic power, you still get something it's like an oversampling of this what we started this continuous wavelet system. So we basically, even though it doesn't look as pretty, it's the same kind of idea. basically by shrinking a function down on its frequency domain, it's the same idea as just now taking the original function we started with, but shifting it by more. So now we're considering more translations. Is this clear? Yes? No? So this is why something that seems so non-intuitive. We have a function, and if we take the system's dialects and translations, the wavelet system, we're not getting a frame. But then if we just shrink that function on the frequency domain, and then take that inverse Fourier transform and look at these that wavelet system, then we're actually more likely to get a frame. And this is kind of the hand-wavy reason why that's happening, because we're now sampling the space more frequently. We're taking more readings. So it doesn't seem to make sense geometrically, but this is why. Okay, so you want to go to back? Okay. And showing that this works, basically, so this was that, the function that we started from 4, where we didn't get any frame whatsoever. There was no lower frame bound. If we shrink it by a factor of 8, then, okay, if we shrink it by a factor of 8, then we end up getting a frame. So we have a frame with frame bounds, so the shrinking actually did that. Next example. So this is, okay, this has a lot of symbols, so it's basically a generalization of ideas. So now all we're doing is, instead of, we're shrinking this, this canonical 1D set, but we're just saying basically that shrinking is just, we're now making it minus a over 2, and then a is just smaller than 1/2. So it's the same thing as shrinking the set. So what ends up happening here, which is really amazing, is we get a frame, but we now know the exact lower frame bound. So when we shrink it, by an epsilon, we could make this like 1/2 minus a million, minus 1/2 plus a million, or 1 millionth. Then we actually can, there's no longer a bound. We know precisely what that lower frame bound is. And then the upper frame bound. But we still have this issue where the frame bounds stop. So it's still, the frame bounds are still constant. But what is also interesting, so you might be asking, well, does this lower frame bound that we compute, was that in the original range we had? Because if you remember, so we're able to estimate that the lower frame bound was between 2/9 and 1/4 before we shrink it. But now we're able to compute that the actual lower frame bound, once you shrink it, is 9/20, which obviously is not in this range. So we can say specifically that we improved the lower frame bound. So actually, why don't we just go back a few slides, because this is me not having gone through this and organizing it well. Keep going. I'm gonna kind of show you these functions again, so it makes this stuff makes a little more sense. It's way back here. Okay, forward. Okay, forward. So the full slide here. Okay. So remember what we had. So this original function, this right here is giving us a bound on the upper frame bound. Okay. So what happens if we are shrinking a function? It's on its frequency domain. Then these cross terms right here, where this k is non-zero, are going to disappear. So if you go back over here, so for this L tilde, if you smooth some L tilde with frequency, with just convolution, then you get the support, which is this L tilde plus, some epsilon, right? So we start with the L tilde, and then the support we end up getting kind of has a fudge factor around what we started. So the support's going to be larger. But then what happens, well, when we shift this function around by integer translates, we get overlap right here. So we shift this over by an integer translate. And now, this new smooth support is overlapping all over here. And so, basically we're getting these terms right here are non-zero. So if you go forward one more. Okay, so if you'll realize then that means that if we don't have any cross terms, if when we do all these integer translates it doesn't overlap, then this function right here, this phi hat of all the dilations, go back one, is the same thing as this function, and it's the same thing as this function. So that's why this frequency shrinking, if we make it so that the domain now doesn't have this overlap, so if we now start off where we start off with say minus 1/4, 1/4, and we do some smoothing, well if we shift this over by 1, the domains still aren't going to overlap. So if we look at this phi hat of, let's say, x, the phi hat of x plus 1, 0, if we're shifting it this way, that's just going to be equal to 0 because the support of this and the support, which is this right here, and the support of this don't overlap. So this cross term goes to 0. So that means that this function is equal to this function is equal to this function. So that means when we take the supremum, the maximum of this function, then we get exactly what b is, because now this is equal to this. And when we take the infimum of this function, we get this is equal to this, because these are now all the same function. So maximizing this function just gives us the exact frame bounds. So this is more mathematically why we can actually figure out exactly what the frame bounds are when we shrink on the frequency domain. Okay, so now you gotta click, 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 click. Okay. Back. Nah, I don't care about this. Okay, forward. Okay, so now, all right. So that frequency shrinking solved our problem of being able to figure out the frame bounds. And it also allowed us in some of those cases where when we were doing smoothing, we weren't even getting a lower frame bound at all, right? We weren't getting a frame. But it still didn't fix the problem of the fact that if we're convolving with these approximate identities, so these bump functions that are getting closer and closer and closer, still the frame bounds weren't changing at all, right? So we want to give that a name. So if we have some sort of psi, which is a partial frame wavelet, and we have a sequence of some sort of frame wavelets or Bessel sequences with certain lower frame bounds, where these generating functions, these wavelets, these frame wavelets, are converging to our partial frame wavelet in L2, but the corresponding frame bounds are not converging to one from above or one from below, then we say it's a frame bound gap. And by Parsifal's equality, we can consider this convergence to be on the frequency domain. So by the results we had on approximate identities, it's actually true that we had something stronger going on. All the examples we had before, we had convergence on the frequency domain for every single LP. Remember, LP, p is equal to 1, all the way up to but not including infinity. So we had these functions that are getting close to our partial frame wavelet in almost every type of convergence except for uniform, but yet these frame bounds weren't moving after a certain point. So it doesn't make any sense, don't really know why it's happening, but now I've given it a name, and when I ask, well, can we do something a little more general than just examples? Because those are some whatever, there's some examples down, and it ends up can show that this does happen more generally. Okay, well I guess I'll just say this. So this is just notation that whenever you see the m with the subscript in the parentheses, then it means that I'm doing this what's called L1 dilation. So I'm just multiplying by m on the inside and multiplying by m on the outside. And also notation, if we have some function, some wavelets, Parsifal frame wavelet set, and we're smoothing it, we're going to just call that the b hat m when we're smoothing with the g. Okay, so I call this one the boxy torus result, because it has to do with these types of shapes right here, right? These squares with holes in them, or cubes with cube holes in them. Okay, so here are all these this hypotheses. Basically, what we're saying here is we've got this basic frame wavelet set. It's the partial frame wavelet set. We've got the box with the box hole in it, and we've chosen our A to be strictly less than 1/2, so that when we smooth it, we don't get that overlap with the shifting that we realize is causing a problem. And now let G satisfy the following condition. So this G is going to be what we're going to convolve with, what we're going to smooth with. So we want G to be as general as possible. We want to see how often this type of thing happens. So we're just saying that G has some support inside some box, but that box contains the origin. G integrates to 1, just like an approximate I did it. So we basically want, so the way that G is supported, basically, just do this right here. This is loosely like saying if we've got some box supported G, or supported G is like, okay. So here's the supported G, which is contained in this box right here. So we've got the B1, C1, B2. Basically all we're saying, so it's contained in this box, and we just want to make sure that G has some positive stuff going on in these little corners. It could probably be done in more generality, but this makes the it makes everything work out right. So you might be able to do it with less generality, but which basically kind of makes sense. You kind of fit the tightest box around the supported G in such a way where you get these just something going on. So it integrates, G integrates something non-negative here and here. So that's all this is basically saying. So we're going to smooth, we're going to take our partial frame wavelet. So we're smoothing on the frequency domain. So we're taking this indicator function, we're smoothing with this function, which we now are going to be dilating, like to make an approximate identity. And for stuff that satisfies this stuff, then we get a frame with these frame bounds. And these frame bounds are basically uniformly bounded away from 1. So no matter how big of an N you choose, the upper frame bound is not going to go past this beta that's strictly greater than 1. And no matter how big of an N you choose, this upper frame bound, or lower frame bound A, is going to be bounded away from 1. So we're getting the same type of thing that happened before, but in much more generality. Just a quick sketch of why that happens. Oh, so, sorry, quick comment first. So the quick comment is, so any non-negative function which integrates to 1 and has a support that's on some rectangle, like would satisfy the hypotheses. So the hypotheses are just kind of generalizing that idea. So you could just take anything you wanted with the rectangular support. And the result holds true whether or not you're doing integers or real smoothing. But the sketch is basically like, since M is large enough, and there's that long list of if M is greater than all these things. Since M is large enough, we can apply some of the preceding theorems to conclude that phi of M is a frame. Basically, we're not going to end up getting these overlaps right here since we're smoothing it out. We started with sets that are not touching each other, and then this boundary right here is going to be small enough. That's what that M being large enough means. And so we can use this to its frame, and then because we know these bounds, because we've eliminated other cross terms, we can get the Chewy, we can estimate these Chewy and Chi bounds. Basically what we're doing is, since it's in generality, we don't know for sure, but remember we now know that the upper frame bound is the sup of this value, and the lower frame bound is the inf of this value, since we've eliminated the cross terms. So that means I can just choose some value, and the upper frame bound is going to be bigger than it. That's basically what it is. It's just kind of a good educated guess that ends up working out. That there's a particular gamma that for all of those cases before, that one gamma will give you a value that's bounded away from 1 regardless of your node. So corollary. So this is actually kind of interesting. So we're doing the same kind of thing. We're starting with the boxy donut. But now we're going to start with a function that's just one-dimensional and has a support in some rectangle, integrates to 1, and that same type of thing. That at the end of the rectangle and then at the beginning of the rectangle, it has non-negative support. So it's just like these corners right here. And so what we're going to do is we're going to define g of d to be the tensor product of these, which just means in every single direction, our function is g. So g of xy is equal to g of x times g of y. So now we're just going to be smoothing with this. And what's interesting about this is what we end up getting is the upper frame bounds as you increase the dimension actually converge to 2. So as you increase the dimension, you're actually basically getting worse results. Like when you smooth, you're getting further and further away from a parsable frame wavelet, and there's kind of nothing you can do about it. They're going to increase. Right? So next, okay. So kind of the proof sketch using the similar type of methods from the preceding theorem, which I didn't go into any of the details, but we can actually. So that choice I said, if you choose a gamma correctly, if you choose your gamma correctly, then you can show that this is a value of this, and that this is a value of this. And so then if you take this limit right here, then you end up getting that this is going off to 2. And these are bounded above by 2 for a certain reason, but that forces it. It means they actually are going to 2. Okay. So the one last kind of frame bound result is, or frame gap result, is trying to generalize this to more one-dimensional wavelet sets. So now we have just an arbitrary partial frame wavelet set, okay, relatively arbitrary. It's a countable union of intervals, which there actually do exist these weird Cantor-like sets that are wavelet sets, but we're going to ignore those. So this is basically about as general as you can get when you're not trying to make something that's ridiculous. So now we have we have a non-negative function which is integrating to 1, has support in this just some sort of interval that contains 0, and we're doing the smoothing. We're choosing our m large enough, and so we're still going to get this frame bound gap. So basically this is saying that even if we're not looking at this very specialized case, we look at a very large class of wavelet sets of 1 dimension, then smoothing with approximate identities, even though yet again this is approaching the original partial frame wavelet set in the frequency domain at every LP but L infinity, we still get this frame bound gap. So this has been a lot of like, hey, all these things are happening that shouldn't really happen, but they're happening anyway, so hope it was enlightening. So the very last thing, though, is okay. So basically, all this is saying is Ben Hahn, for his master's thesis and for another paper, did some work where he actually did smoothing of sorts, where he started the partial frame wavelet, but he actually got wavelets that were compactly supported and infinitely differentiable. And so basically what it's saying is you have to start with some partial frame wavelet set that has this delta L, which is strictly positive. And then if you do that, there exists some sort of, there exists a partial frame wavelet that's smoothing or compactly supported. So notice I actually said this is a partial frame wavelet. So he takes sort of partial set and he does smoothing and he gets a partial frame wavelet.
What's that?
So you're like, wait, this doesn't make any sense. That totally flies in like what you're just saying, right? Or wait, go ahead and ask your question.
I'm gonna say, what's the S? S of R?
Okay, so the S is like almost as good as CC infinity. The S is a Schwartz space, and it's all infinitely differentiable functions, so they're all smooth. But they're not necessarily compactly supported, but they they basically decay faster than every polynomial. So they decay faster than whatever x and whatever x squared, and so on and so forth. So it's like, so basically if they exponentially decay, then that would work. So like a Gaussian would be a prime example of an element of Schwartz class. And it ends up actually, the Fourier transform maps Schwartz to Schwartz. So essentially what's going on is he constructs this thing on the frequency domain that's smooth and compactly supported. So if something's smooth and compactly supported, it's obviously in Schwartz. So that's how we know is that also on the other domain it's also Schwartz because he's just taking the Fourier transform. And so the question kind of arises though, it seems odd because you think, wait, so all these previous slides we've had is all showing that when we do this smoothing, we're getting frame bounds that don't approach 1, right? And now here, he smooths and he gets something where it's not even that they're approaching 1, like he actually gets a new partial frame wavelet that's smooth. So basically what's going on is he proves the existence of such functions with kind of this, that he proves that there exists a certain type of bump function, so a certain type of function in CC infinity that can be manipulated, and you can kind of use this, and so you were basically, you think about like you're replacing this this characteristic function with this smooth bump function that's like 1 most of the places where the characteristic function is 1 and 0 most of the places where it's not, and then kind of smoothed out. But it's not constructive, so you couldn't actually necessarily use it, it just shows that they exist. But what's interesting is this also shows now that these functions that he's shown to exist can't result from convolution. So he uses this long constructive process, but because of the results we have now, we now know that like you can't get these smooth functions with convolution. So these functions that he has now, we now know this about them. Another quick comment, this shrinking technique, so shrinking on the frequency domain means that we can now take one of these sets from Dr. Benedetto's construction and shrink it down and apply this. So we can now show that any of these sets, once properly shrunk on the frequency domain, can be used to do this. I should point out, and I didn't get this on the slides yet, so if you notice here though, it's only over R, and it ends up, things go wrong, horribly wrong when you go into higher dimensions. So you can try to generalize his result to higher dimensions and it totally collapses. And so you end up getting things that are actually, well, not totally collapses. When you try to generalize this, you get functions that are partial frames using these bump functions that he said existed, but they're no longer infinitely differentiable. In fact, they're not even, they're only continuous. They're not actually differentiable. So this is something I still need to write up though, so that's why it's not on the slide. Okay, next one. Okay, so just skip this. So this was that construction that I said before, one of the possible constructions of a that C infinity bump function. So it's compactly supported. You start with this function right here, and you shift right here. And what does that function end up looking like? So this B and this A correspond to an inner and an outer radius. So for this function right here, basically this creates a function which is 0 bigger than b, 0 less than negative b, and you have 1 in between, and then there's a nice, this is continuously differentiable between the a and the b. So we have a nice actual construction. And so one of the things that I've recently written on paper, but not yet gotten into LaTeX, is that, so basically you can use these functions to get you smooth frames which have frame bounds which converge to 1. So what's nice about this is meaning that basically now you're thinking about, well, so this is like A, and this is A plus 1 over m, and this is minus a minus 1 over m. And now we're using this to replace something with a bump function. So now this is our negative 1/4, negative 1/8. And then now we have over here the 1/8, 1/4. So basically what I'm trying to say, this is like a very hand wavy thing. But so let's say we start with that partial frame wavelet, which is the negative 1/4, negative 1/8, and 1/8 for 1/4. And so now instead of taking just the characteristic function right here and then smoothing it with convolution, which obviously yields problems because we're not ever going to get anything close to partial frame, we'll just replace it with one of these functions that's used all the time in like manifold theory, differential geometry. And if we just replace it with one of these functions and we squeeze basically that a and b value closer and closer and closer together, then if you then compute the frame bounds, then the corresponding frame bounds actually converge to 1. So we beat this frame bound gap problem. And what's nice is, unlike Han's result, which is very beautiful and he did it just for his master's and it was very many years ago, but it's not constructive. I mean, this is, you have the function right there. You can construct it so you can make these. But also a side comment, because of the other result of frame bound gaps, we also now know that these functions that are widely used in pure mathematics can't actually be the result of these convolutions. So it's kind of just another result. And I've talked a whole lot, and yes. You have any questions? Are you guys like awake still?
So we can use a spline to close the gap, the frame gap in this one.
So I'm not saying splines, I'm saying this function that's these functions right here. So we take f to be that exponential function, and then we shift it, and so each one of these corresponding to a certain a and b corresponds to a single bump. So we're kind of summing up 2 of these functions. So we take a function and we sum it up, and then we're doing that. So this convolutionally smoothing with splines didn't help, no matter how high dimension this spline was, or no matter how smooth this spline was, it didn't improve the situation. But here, this replacement method, because the convolutional smoothing just doesn't work, the replacement method with this will actually work, and it is constructive. Of course, I don't really know how much someone really wants to do computations with this function. I mean, it's very easy to write, but that doesn't mean that it's actually going to ever be used. But it is constructive, which I guess is like a feather in my cap or something. Constructive is a buzzword for I can write a formula for it, but no one's going to use it. Yeah. Okay. Anyways, any questions? Yes? No?
How fast is this convergence line for frame bounds?
So we're getting something that's on the order of like, it's loosely on the order of 1 over 1 plus e to the minus 1 over c, for like one of the frame bounds.
Where t is
Oh, sorry. I messed that up. Let's see that. Sorry. There is a t in there, but that's because you're proving the bound for each
really
one.
quick.
What?
That's nice. It's really quick.
And so actually this was, before I just decided to try to hand compute the bounds, like, well, I don't have it up there, but before I decided to hand compute the bounds for what these functions will get, I was trying to use, like, Mathematica and other things, and it was just choking because the convergence was actually so fast that it didn't know what to do. Like, because basically you had to divide out by stuff, and they were getting so close to the original function that bad things were happening, and it was jumping all over the place. It was driving me nuts, and then I just realized I could do it by hand with like calculus. It's exciting. It's funny how that works out sometimes. Like sometimes like something's really hard and you just sit down and do it with like first semester calculus. So
Like the papers you cited, especially the recent ones that you did, are they easy to find?
I could send you the other one because right now it's the journal has not yet been published.
Okay.
There will be a special edition of Acta Applicanda Mathematica on Wavelet sets. This other result I haven't teched up yet, so if you want to give me your email address as soon as it's teched up and not like this, then on the backs of like flyers and stuff like that, then yeah, I'll send that to you. So, and actually I should say like half of that paper is already written. It was about what the higher dimensions for this result have been on this result. But.
So a lot of times, I guess engineers will like chop off like a threshold function to get up to the Fourier transform.
Mm-hmm.
So like what kind of thresholding or what was like the size of the support of like Fourier transform measure as you vary the threshold? You know what that would look like?
Size of the Fourier support? I mean, the Fourier support
So
size
you
is
invert you invert the Fourier transform and you get this function, right, in time. And so depending upon like the M you've chosen, what kind of support can you expect to find if you're varying the threshold?
Support on what side?
The time side.
And what are you doing with this thresholding? I mean, if we're starting with something.
I'm basically setting the function to 0 where it's below some threshold.
Okay. But I guess what I'm saying is, I mean, these functions look basically like this. They're compactly supported. So even with the threshold, I mean.
No, when you take the inverse Fourier, so you inverse Fourier transform this thing, right?
Okay.
And you get a function in time space, right? But of course, it's got really fast decay. So, but what's the size of the support given, say, a certain threshold?
I have not done computations with that, but because of just this relationship between decay and support. No, it's definitely not going to be finite, and that's due to the uncertainty principle, actually. So if you ask me compact supporting, but okay. So what I was going to say though is that because of the relationship between smoothness on one domain and decay on the other, like. I mean, I haven't done the numerical computations, but basically these functions right here that are smooth, they're infinitely differentiable. They're going to be, as far as thresholding, I mean, they're going to be squeezing the most up. If that makes any sense. That smoothness is going to give very fast decay. Now, quantifying that, no, I've not done that at all. But yeah, I mean, obviously, the smoother you're getting on this domain, the faster decay is, so more information is going to be contained in the threshold improvement.
Kind of a more general question. Just all these constructions with like characteristic functions of sets on the over on the frequency side. Do you have a sense that these are just like building blocks to a more general wavelet theory that, because it seems like it's just a narrow subset of the possible wavelets you could construct.
They are very much a narrow subset. But as far as building, I mean, really, how do I say this? So some of the ideas of, so this wavelet set, and you can see some of this, but the orthonormal wavelet set, we know it's a wavelet set if it's tau congruent to this and delta congruent to, this other set. So if you think about supports of wavelets and how much information is contained in certain areas of support, like, so for example, something like this, like most of the support is contained in here, there's a little bit here, and then it's here everywhere else. Then a lot of these formulas, these Dobishis and Christensen and the Chuishi Jing formulas that give you these frame bounds of the wavelet systems, can be almost thought of as quantifying how much support, like how far away is the support of your wavelet from being this wavelet set construction. And you can kind of think it because like basically what you're doing here, you're taking all the dilations and you're summing up all the values. So you're saying like, if I shrink this in and stretch it out, how different is it going to be than if it was just flat on this piece? Am I going to get big spikes? If I'm getting big spikes, then that means that there's a lot of support that's contained in a way that wouldn't be in a wavelet set. And then similarly for this. So you can almost, yeah, if you wanted to, you could think of those formulas as kind of like a way of generalizing this idea from wavelet sets, of measuring the overlap of the dilations and the integer translations and how they interact with each other. But as far as like using them to construct other wavelets, I mean, other than these constructions right here, I mean, some sort of smoothing, there's actually been 4 wavelet sets which are associated with an MRA, for orthonormal wavelet sets associated with MRA, which not all of them are. The Journet wavelet does not have an MRA, while the Shannon wavelet set does. But you can do a smoothing process using the MRA structure. So you use like the filters and you can smooth the filters associated with that MRA. And then there's a thing called a generalized MRA, which you can put with the Journet wavelet. So you kind of do smoothing like not of the actual wavelet on the time or frequency domain, but of these like associated functions. And then you can develop other wavelets. But yeah, I mean, other than just modifying what we start out with, there's not. It's just especially for higher dimensions, like you can construct wavelet sets easily. It's not necessarily easy to say like, I want a wavelet for like over L2 of R3. Like, there's not really an intuitive way necessarily to start with that. But yeah, which is why these came about, was that it solved that problem. They didn't think that there was a a single generating wavelet that could, and a single wavelet could generate a orthonormal basis over L2 of R2, or L2 of R3, or L2 of R4. So it took these wavelet sets to kind of prove that that wasn't the case. Any other questions?
Can we get the slide?
Yeah, I'll do that.
Do you want me to put them up on the web page?
Yeah, it will be there.
Okay, I'll make a copy of it and put it up there.
And one thing I didn't mention, which is very interesting, so the examples where we had these frame-bound gaps, right? We're smoothing with approximate identity, and we're getting frames. We're getting that the frame bounds are not approaching 1, right? If you instead do the same type of smoothing, the exact same type of sequences of approximate identities, the exact same like sequences of functions that I was trying right there, but instead you smooth on the time domain, you're smoothing the hard wavelet on the time domain, then what you get, you actually do get, with that type of smoothing, you actually get wavelet frames that are that have bounds that are converging to 1. So it's interesting, there's something weird that happens when you do the smoothing on the frequency domain versus smoothing on the time domain. Because it works completely fine, say, on the hard wavelet. There's like no problem. It's very easy. It's a 2-page paper someone wrote a few years ago. It just happens. It works. So something weird is happening. Disparity between the time and frequency domains.
Can we have that paper?
What?
Can I have that paper?
That paper?
Yeah.
Well, yeah, so yeah, I mean, I can definitely send you the sources. I'm just trying to think of the best way to like include the proper sources and with the paper. Maybe I'll add an extra slide on this.